What happens when you find a wormhole in spacetime? It doesn't just connect two points. It fundamentally breaks our standard understanding of how quantum gravity relates to singular quantum field theories. This paper explores how treating gravity as an ensemble of theories might solve this paradox. Let's begin by looking at a persistent issue within the mathematics of 3D gravity calculations. When physicists calculate the density of states for 3D gravity using only smooth geometries, the results often appear non-physical because they become negative. The authors argue that including wormholes fixes this, but it implies gravity is dual to a statistical average of theories, not just one. To formalize this ensemble, the researchers utilize the framework of topological quantum field theory. In traditional holography, we usually expect a one-to-one match between a bulk geometry and a boundary theory. This paper proposes a TQFT gravity approach, where summing over all possible topologies corresponds to averaging over many different conformal field theories. But how do they define these specific boundary theories? The authors use a process called Lagrangian condensation, which involves gauging, or identifying, certain topological defects called anyons to reduce the bulk field theory down to a specific boundary state. With the boundary theories defined, the next challenge is calculating their average using geometry. The method involves starting with a surface that has an arbitrarily large number of holes, known as high genus. In this extreme limit, the different boundary theories become mathematically distinct, or orthogonal, allowing the researchers to project the system down to simpler shapes, like a torus. Here is the central discovery of the paper. When averaging these theories, they are not treated equally. Each theory is weighted by the inverse size of its internal symmetries, meaning that highly symmetric universes are statistically rare in the gravitational ensemble. This result connects physics to a deep mathematical identity called the Siegel-Weil formula. Physically, it implies that the baby universes created by wormholes form the exact Hilbert space needed to describe the ensemble of boundary theories. While powerful, this approach has limitations. Summing over every possible geometric twist involves infinite terms that require careful regularization. However, it successfully demonstrates that pure gravity tends to suppress highly symmetric states in favor of more typical configurations. To learn more, head to emergentmind.com.